The next speaker is Dr. Xiaogang Chen. He's a senior lecturer in technical textiles, UMIST in UK. He received his bachelor's and master's degree from Xi'an University, China, and a PhD from Leeds University, UK. He joined the UMIST in 1994 and has been doing research in protective textiles, automotive textiles, medical, construction textiles, etc. So please welcome Dr. Chen.
Thank you, Professor. First thing I'll do is to my listening info. By the way, my computer is quicker than this. Yes, while I'm preparing for this, I can just tell you that in UMIST we have a technology group. In the group we are, well, one of the activities we do is actually the 3D fabric manufacture. We have produced the 3D fabrics using the knitting technology, non-woven technology, and weaving technology. So what I'm going to report to you now is actually part of our 3D weaving woven fabric research. Right, the 3D woven structures we have generated, including 3D solid structures, 3D hollow structures, and also 3D shell structures. So what I'm going to talk now is actually the weaving and the evaluation of 3D domed structures, which is a shell. Okay. So what is a domed structure? Okay, it is a shell, but yes, here it shows you one example, which is so you can see, this is a fabric, okay, with a dome. So we produce the dome fabrics using different technologies. This particular fabric, okay, is woven flat. And then because of the special properties of the inner structure, okay, so it can be very easily domed into a figure like this. And because of this one, I just like to tell people that I was in the local newspaper, okay, so which is very nice for me. And dome fabrics can be used in many different applications, okay? It can be used to make composites, okay, to eliminate the molding process, okay, eliminate the molding process. The second application I listed here is actually the helmet making. Okay, I am doing a research project with the police in the UK, and that's to replace try to generate a new method for making helmets. Currently, for making helmets, okay, you will have to use 9-10 pieces of fabric to patch the head shape. Well, as you can see, in one of the project we're doing, you see this is one piece of fabric with just one cut in the middle, and then you see it can be made into a dome shape. And also female body armor, okay, female body armor, you can use this technology to do that. And if you like, you can do bra cups, and so on. Okay? So the current method used for forming a dome shape is, well, in textile, is either molding. Okay, you mold it. I'm sure you will have excessive fiber strand because you will have to press the fabric too hard into a 3D shape. Now the second method is actually folding. Okay, you fold the fabric, okay, to form the 3D. As a matter of fact, some of the police forces use ladies' body armor using this method. Okay, I saw that, and I was told that was not comfortable to wear at all because where the folds are, you see, they use up to 30 layers of fabrics. If you use a folding technique, then you see somewhere it will have a very, very thick ridge. That will be very uncomfortable. And then third method which is used is cut and sew. Okay, you cut it, cut the fabric, and then get them together to form a 3D. And then the last one I listed in here is actually patterning, or should be patterning. Okay, patterning and patching. Okay, cutting the fabric into pat and then patching, like people who are making like the helmet picture. Okay. Right. So I'm going to talk about two methods which we experimented on. The first one is what we call it the patchy design. Okay, we know in textiles if you combine different weaves together, then you can make the fabric become uneven. Okay, polycomb fabric is a typical example. If you extend that idea to a larger scale, then you can have uneven surface to form a dome shape. As you can see from these slides, okay, we use the plain weave in the middle, in this circle, okay, and then a 2 to 12 in the middle circle, and then out circle we use a 5 and satin, okay, and then the configuration of these three different types of weaves are different, so they occupy different area, okay. On the loom, you see we can arrange the circles either like this or like that, okay. Then when the fabric's made, well, it is a 3D dome structure, as you can see from there, okay, the dome structure. One of the problem we found in this is that if you design the dome to be too big, then you will have a problem in weaving because the tension will become very uneven. As you know, in weaving, if the warping tension is uneven, then you can't weave for too long. Otherwise, some of the warp ends will break. Right. Then, because of that, then we experimented on a completely different way of making dome fabrics. The device we developed, we call an add-on device. Okay, we call it add-on because it is we modified the conventional loom, okay, by adding this part on. Okay, if you don't want to make dome structure, dome fabric, then you get this off very easily. If you need to produce that kind of structure, you just put this on. So basically, these two diagrams shows you the normal take-up arrangement and the modified take-up arrangement. Okay, the main thing is actually here. We have developed a profile chain to go around the profile roller. Right. So this shows you the details about how the profile chain is developed. Okay. So you have dome in there with the height, whatever height you would like, and then you see eventually you will have to slice it into different profiles so that you can use it. And then this shows you the design of the each profile. Okay, here you will have to have some holes in there so that it can be moved by the turning of that profile roller. And this is the driving illustration of the driving of the profile chains. Okay, and some kind of calculations down there. And also, you must use multi-beam for weaving the structure. because as you can see, in the middle of the fabric, okay, in the middle of the fabric height, well, the fabric is domed in there, so you need more warp yarns. While on the sides, the ground area, okay, you need less warp yarn supply. So in our research, in our experiment, we use 3 beams to provide the warp yarn, okay, so that we can have the dome shape. And then accordingly, we designed fabrics, but 2-dimensional fabrics, and a double cloth, treble cloth, and a 2-layer angled interlock structure, and a 3-layer angled interlock structure, okay, using this device. And this is a picture of one of the results. As you can see, because of the use of the add-on device, you see we can produce a dome smoothly. Okay, there's no obvious ridge surrounding it, so it can be useful for many different applications. Right. So that's the production of the dome structure. And also, obviously, another thing is to find out how formable of the fabric is to create domes. So, in order to evaluate that, we have defined the dome index. Okay, the index is a percentage. That is the DI. DI is the fabric density for the flat bit of the flat areas, and the DM, that is the fabric density for the domed areas. Okay, DI minus DM over DI times 100. This is the dome index. So we used this index as one of the measures to evaluate the formability of domes. And in order to take the density, we divided along the fabric 5 different areas, and also across the fabric 5 different areas, and along the fabric 5 different areas. We measure the density from each of these areas, and this is the actually the density, vector density change along the length. Okay, we have 5 different stages before the profile starts, start of the profile, middle of the profile, end of the profile, and then after. Okay, as you can see, the density of the vector density here change from normal down and then back to normal again. So basically, that is what they showed us. While that's the vector density situation, on the warp density, not surprisingly, you see, there's no substantial change. There's no substantial change. Right, the dome index. Okay. So dome index has a very good relation. Well, it's a very obvious relation with the vector density of the fabric. Okay, this is an example. This is the plain fabric example. For other fabrics, it shows us a similar trend. Okay, and corresponding to that, you see this is the relation between the dome index and the fabric density in the warp direction. Okay, so the relation, because as I said, you see the warp density was not affected by the dome formation, then the relation here is not quite obvious either. Right, so the dome index has obvious relation to the relationship with the fabric structures. Okay, so plain is the most solid in this case, and 6N satin is the most loose structure. So as you can see, the looser is the structure, the easier is for the fabric to form the dome. Okay, and that's the that's to compare the different parts of the fabric: the ground, side, and the top. And then you see the dome index comes down for all these 3 parts of the fabric when the vector density per layer for a double layer fabric goes down. Okay? This is the fabric for 3-layer. This is the relation between the dome index and the 3-layer fabric. Layer 1, 1 layer, 2 layers, 3 layers. Okay, so as the number of layers go up, the dome formability comes down. So that's easy to understand. And then this one shows you the 5 minutes. Okay. So it shows you the angle interlock situation. Okay. angle interlock. Well, the dome index comes down when the weft density increases for all different fabrics. Okay. The second evaluation method is actually moldability tester. Okay, we developed this for this purpose and for mirroring dome structures for different fabrics as well. Okay, so basically we have three parts. Okay, the base, the top, and a probe. So this is how you would use. Actually, we have two methods of using it. This is method 1. Without going into the detail, you can find it from the paper. Okay, method 2. You use the top in a different way. Okay, and then the result is dome depth against the wall and weft density there. So you can see the relations. And this is a twill fabric. Shows the relation between the dome depth and the weft density there as well. And similar densities. Let me quickly go through these. Okay. Right. So now we have used two different methods. One to evaluate the dome effect. Okay. One is dome index. One is dome depth. So that's the part of the of my presentation. I just want to show you the correlation between the two methods. As you can see, for plain fabric, it works well. For twill, it works well. For satin, it works well. Multi-layer works all right. Yeah, it works well as well. And angle interlock works well as well. Right. So come to the conclusion. We have produced dome fabric using two different ways, two different methods: patching design and an add-on device. And then the two dome evaluation methods are used. Okay, that's the dome index and dome depth. And what we saw is that the higher the density, the smaller is the dome effect. The tighter is the weave, the smaller is the dome effect. Okay, and also we have seen there's a very good agreement between the dome index and the dome depth. Thank you very much.
Questions? Any questions? What is the largest size dome you are?
Yeah. Well, the size of the dome is actually dependent on the profile. If you design a bigger profile, then you can do a bigger dome. The one we use, as I showed, is 25 millimeter. That's what we do. 25 centimeter. And I believe if you use a larger dome, a larger profile, then you can produce a larger dome. Okay, thank you.